In this video, I will talk about conversion of first kind, integral equation of first kind to second kind. We will learn about the conversion of Volterra integral equation of the first kind to the second kind, how we convert that. Sometimes it becomes more easier to solve a integral equation as a second kind than the first kind. So our Volterra integral equation is f of x is equal to 0 to x kxt, which is a kernel u of t dt. This is equation number 1. So to convert the integral equation of first kind, this is first kind since there is only one unknown, which is in the integration, which lies in the which is in the integrand of the integral equation. We differentiate that, we differentiate equation 1. So we apply the Leibniz rule. We have df by dx, and on the right hand side d by dx 0 to x kxt u of t dt. We will apply the Leibniz rule now. In Leibniz rule, what we do, we differentiate the right hand side integral, first taking the upper limit dx by dx, then put that upper limit into the integrand over here. That will be kxx u of x. Then we have the lower limit. We take a derivative of lower limit and put kx0 u of 0. Then we have the derivative of integrand, which is partial by partial x kernel u of t dt. So that was the Leibniz rule. This term becomes 0. So we have f dash is equal to kxx u of x plus 0 to x partial k by partial x. Since k is a function of x and t, so we need to use the partial derivatives u of t dt. Now the only thing is left over here is to separate out the unknown function u of x. So what we do, we divide this whole equation by kxx. So 1 over kxx f dash is equal to u of x plus 1 over kxx 0 to x partial k by partial x u of t dt. Now we just keep u of x on one side. So we have u of x is equal to 1 over kxx f dash minus 1 over kxx 0 to x partial k by partial x u of t d of t. So this is the Volterra integral equation of second kind. Why this is second kind? Since there is one unknown over here, and another unknown is in the integral. So there are two unknowns, so that is called second kind. And the limits are variable, so we have Volterra integral equation of second kind. And we need to remember that kxx should not be equal to 0. If it is equal to 0, then there is no sense that we can get the second kind. So let me just solve one example for you over here. Example, solve x square plus x cube by 6 is equal to 0 to x 2 plus x minus t, and we have u of t dt. This is Volterra integral equation of first kind. First, we need to check if we want to convert this integral equation 1 into the second kind. First, we need to check either the kernel is not equal to 0. The simple test is take kernel. We have the kernel over here. The kernel is 2 plus x minus t. So that is 2 plus x minus t. What we do in the kernel, we replace this t with x. We get 2 plus x minus x is equal to 2, which is not equal to 0. So we can convert equation 1 into the Volterra integral equation of second kind. Okay. So what was the procedure? The procedure, either you can use this formula or just differentiate equation 1. So we first identify f of x. I just want to use this formula since it is a bit easier. F of x is x square plus x cube by 6. This is our function. We take a derivative. We take a derivative f dash x 2x plus 3x square by 6 2x plus x square by 2. This is f dash x. Now we put this f dash x in this equation. We already know the kernel, the, kxx. Then we need to take a derivative of kernel with respect to x. What is k? This is k. We take a derivative of this with respect to x. So we have partial k by partial x. That will be equal to 1. All other values will be constant when we take derivative with respect to x. So we are almost reached at the Volterra integral equation of second kind. So the solution, the second kind is u of x is equal to 1 over 2. F dash is, what is f dash? F dash is 2x plus x square by 2, this value. Then we have minus 1 over 2, 0 to x. What is partial k by partial x? This is 1. So u of t dt. Now we simplify that. U of x will be equal to x plus x square by 4 minus 1 by 2, 0 to x, u of t dt. This is Volterra integral equation of second kind. How you will solve that equation? There are different methods available. What we do, we apply modified decomposition method. Modified decomposition method. In this method, we start with any initial approximation, and that initial approximation can be chosen from this function f of x. It can be x, it can be x plus x square by 4, whatever the function f of x is. Suppose we choose u naught is equal to x. This is our initial approximation. In modified decomposition method, we have the formula. The next formula, iterative formula, is un plus 1, and whatever the next value is, the remaining one is, if you have considered u naught is equal to f of x, this is x, then the remaining one is x square by 4 minus 1 by 2, 0 to x, and that is u and t dt. So this is the formula for modified decomposition method. So when we have n is equal to 0, then we have u1 x squared by 4 minus 1 by 2 0 to x u0t dt. That will be equal to x squared by 4 minus 1 by 2 0 to x, and we know that u naught is x, but since it is t over here, so that is t dt, and we have x squared by 4 minus t squared by 4 0 to x. So u1 will be equal to x squared by 4 minus x squared by 4 when we apply the limit, so we get u1 is equal to 0. Similarly, if we use n is equal to 1, then we have u2 is equal to x squared by 4 minus 1 by 2 0 to x u1t dt. Since u1 is equal to 0, x squared by 4 minus u1 is equal to 0, so we get u2 is equal to x squared by 4. Or let me see what I have done. Maybe yes, it is correct. So u0 is u1 is 0. If u1 is 0, so we get u2 is equal to x squared by 4. So at the end we get the u0, u1 and u2. So the solution is we can get another components as well. The solution will be equal to u of x u0 plus u1 plus u2, so on. That's how we get the solution. Okay, so this was about, the main topic was how to convert the integral equation of first kind into integral equation of second kind, and we just converted into the second kind, and then we solved by any method. You can use any method over here, and we got the solution somewhere over here. Thank you for watching.